Hello students, in today's video we're going to be talking about asymptotes, vertical asymptotes, and end behavior. So let's get started. This quick warm-up problem, I don't want you to pause your screen so we can save a little time. We're going to go ahead and start working on these already. Now, a quick thing on end behavior. End behavior actually tells us the behavior of a graph on its ends. So if we were to take a look at a few different graphs, for example, if we were to draw and sketch one, this is going to be your standard x squared graph. Your x to the fourth graph is actually going to come out a little wider. And so if you look at the ends of the x squared and the x to the fourth graph, you'll notice they're exactly the same. We're really just looking at the ends. What do they look like without worrying about the middles? So right here, we don't care about that. So that's what end behavior typically refers to. So let's look at part A. Now, to determine the end behavior, all we need to do is look at the largest exponent for their variable. So in this particular case, 5x to the 7th is the end behavior. It's our typical function for an end behavior. What that means is this graph might have a lot of ups and downs, but at the end of the day, it's going to, because it's an odd graph, it's going to look something like this. Now keep in mind, this is a very rough sketch. Because it has all these extra pieces at the end, extra monomials at the end, it could very well have all these little twists and turns that I'm sketching, but in terms of its end behavior, it looks like an odd graph or a cubic graph. If we take a look at g of x, or part B, it's negative x to the 2012 power. So because it is a even function, it should look like a parabola like so. However, because it has the negative coefficient, it's going to be going downwards like so. So that's what end behavior graphs look like. And that's how we find them for these simple cases. But obviously they're not always going to be simple, and we'll look at those today. So, an end behavior model. Now, this is the formal definition. We're going to go into something a little bit simpler in a second, but I wanted to at least expose you to it. It says the function g is a right end behavior model for f if and only if, that's what the IFF means, if and only if the limit as x approaches infinity for f of x divided by g of x is equal to 1, and the function g is a left end behavior model for f if and only if the limit as x approaches negative infinity of f of x divided by g of x is equal to 1. So basically, we talked about what end behavior models look like. That's both sides. When we talk about right side, that's obviously for the right side, and left side is obviously for the left side. So let's take a look at a real example. So for example 4, we have 3 different types of examples. Now it says find the power function and behavior model for the given function and identify any horizontal asymptotes. So for functions like this first f of x that I'm pointing to here, again, we're just looking at the largest exponent. So here, the end behavior model, or the power function, is a negative 4x cubed. That is the power function and behavior model. When we look at g of x, what we do, because it's a rational expression or fraction, we take a look at the 2 largest. So we're going to look at negative 2x cubed divided by 7x squared. And because this is a fraction, you notice that we have x cubed on the numerator, x squared on the denominator. We can actually cancel out the cube, or we can cancel out the x's. That means we'll have 1 left on the numerator, and we will have nothing left on the denominator. Therefore, we will have negative 2/7 x as our power function and behavior. So just like so. This is the function we're looking for, and it has no vertical asymptotes. I didn't explain, or horizontal asymptotes. I didn't explain why yet, but I'll show you in the next example. So in the last example, the bottom f of x, we're going to look at the 2 largest exponents. So 3x to the 4th on the numerator, and I wrote this on purpose like this because I wanted you to look. you have 2x to the fourth on the denominator. It's not just one on top of the other. So we have 3x to the fourth divided by 2x to the fourth. And you'll notice the x to the fourth will cancel out, and you're left with 3 halves. Now, in this particular case, we have a horizontal asymptote. The horizontal asymptote is at y equals 3 halves. Now, just to point this out, this is your horizontal asymptote because there's no x left over. When you do have an x left over, you can't have a horizontal asymptote because it's a diagonal line. The first one had that x cubed left over, which is a cubic. So none of those functions can be horizontal because they have a different function attached to them. Y equals 3 halves has no slope. It's just y equals 3 halves, and that's your horizontal asymptote. It's also your end behavior function. So let's move on. If we take a look at example 5, this is another one. It's a little bit tricky, but this time instead of looking for power functions for the end behavior, we're looking for simple, basic functions for the right end behavior model and the left. Now, this is a little bit counterintuitive, but we're going to try anyway. Now, if we take a look at this function for f of x, if I wanted the right end behavior model, so I'm going to write EBM just to make my life a little easier. That basically means we want to isolate the right side, and when we want to get that e to the negative x by itself, we divide by the left object. So we're going to divide by x to the fifth on both sides, and what happens there is we can now write this as x to the fifth plus e to the negative x, all divided by x to the fifth divided by x to the fifth, but this time we're going to split them up. So as we split them up, you'll notice that these cancel out, and you're left with that 1, plus you'll notice that e to the negative x has a negative exponent. So theoretically, it should be written as x to the fifth times e to the x and if we look at these as the limit as x approaches infinity, you'll notice that the 1 is going to stay the same. That limit's going to be 1 no matter what. But for the second piece, as x approaches infinity, the 1 divided by x to the fifth e to the x is going to become closer and closer and closer to 0. Therefore, we got our right end behavior model, which is 1. For the left end behavior model, or EBM, instead of dividing by the left object, we're going to divide by the right object. So what we're going to have here is, trying to copy this really quick. In the last example, when we divided by x to the fifth, now we're going to divide by e to the negative x. And the same thing on the right side, or on the other side, e to the negative x. And again, you'll notice that when we have these fractions, this cancels out and you're left with 1. This, because it has a negative exponent, should read e to the x, x to the fifth, plus, oops, that's weird, plus 1 Now, keep in mind, this time, because it's a left-end behavior model, we're going to have x approach negative infinity. So limit as x approaches negative infinity. So because that approaches negative infinity, that again will become e to the negative infinity, x to the negative infinity, plus 1. Again, because these exponents here are negative, that means they're going to be moved to the denominator. Therefore, the limit here is going to be 0 plus 1 equals 1. And that's how we're going to have our left-end behavior model. So I'm going to quickly go through part B, only because you're not going to see this too often. I just want to make sure you're exposed to it. So we have our right-end behavior model and our left. When we do it for x squared plus sine x, again, when we're looking for our right-end behavior model, we're going to divide by the left side. So divided by the x terms, so x squared and x squared. Divide those two values. And when we do the same thing for the left-end behavior model, it's going to be x squared plus sine x, the original stuff, divided by sine x, and these, when they approach infinity and negative infinity respectively, will be equal to 1. So let's look at another example. This is a really important thing. We're seeing the limits as x approaches infinity. Now, what this is saying here is that if we have some function when x is approaching infinity, sometimes they're really difficult to see. So what we can do as a way to see, in quotations, how this function or the limit is, we set f of x to be 1 divided by x. And in order for us to see the limit as x approaches positive infinity, we go towards 0 from the positive side. When we want it to see it from as it goes to negative infinity, we see what the function approaches from the negative side. So we'll do this a little bit slowly. Now, we have this function f of x equals x squared times e to the negative x. We're going to use the graph of y equals f of 1 divided by x to find the limits here. Now, before we start working on it, we're going to rewrite this. Now for part A, as the limit as x approaches infinity, we're going to substitute f of 1 divided by x here. What that means is this will turn into 1 divided by x squared times e to the negative 1 divided by x, like so. Moving forward, 1 divided by x squared is going to be 1 divided by x squared. The second portion is going to change a little bit. So because your e here is a negative exponent, it's actually going to be rewritten. So let me rewrite all of it, actually. So again, because that e has a negative exponent, this is going to be x squared. This is going to be e to the 1 divided by x, like so. So I'm going to move this over here so you can see it a little bit better. Now, for this, as the limit, or for the limit, as x approaches 0 from the positive side, because we're going towards infinity, we are going to substitute these values in. So let's pretend for just a second that our 0, as it approaches infinity, is going to be something like 0.001, or 1,000th. So that would change this to be e to the 1 divided by 1,000th. Now, I just picked some arbitrary number. We could have picked a millionth or something to that effect, but I think this makes our point. So 1/1000th is what 1/1000th looks like as a fraction. That's why we call it 1/1000th. And then e to the negative 1/1000th. Oh, I wrote this wrong. This should have been 1 divided by that as a fraction. I just forgot to write as a fraction here. Now what's going to happen here is this e, or eccentricity, is going to be called, or it's going to become 1 divided by e to the 1000th power, because 1 divided by 1000th is this value. Now, what's going to happen here is both of these values on the denominator are going to get larger and larger and larger. And as this 1000 that we just chose arbitrarily gets bigger and bigger, it means the whole value is going to get closer and closer and closer to 0. So for this function for part A, the limit as x approaches infinity for x squared e to the negative x, that answer is going to be 0. Now let's do the same thing we did for the original problem, but this time we're going to do it as x approaches infinity from the negative side. So we're going to write our fractions like we had. Remember, we had 1 divided by x, quantity squared, e to the negative 1 divided by x. And this time when we're looking at this limit, we're looking at this limit as x approaches 0 from the negative side. So here's how this answer will look. As x approaches x approaches 0 from the negative side, I'm going to rewrite this whole line just so you can see where we get these numbers. Now, here, this is what we started with right here. Now we're going to work on the limits. So, for this limit, as x approaches 0 from the negative side, we need to choose some arbitrary number, which is what we're going to do. Now, last time we picked 1/1000th. This time we're going to pick negative 1/1000th. So this is going to become 1 divided by 1/1000th as a fraction. So make sure you put that fraction so everyone sees it. So 1 divided by 1,000th. And because it was a square, we need to put that square back in there. So squared. And we're going to do the same thing here for the e portion. So that's going to be 1 divided by e to the 1 divided by negative 1,000th. Forgot to put negative 1,000th here too. And again, we're choosing that because it's coming from the negative side, so we have to choose some value from the negative side. So this is what our function should look like for that limit. And now we're just going to simplify this. So if we look at this left value, this one right here, you'll notice that's a squared. So it's going to turn out to be 1 divided by 1,000th, no matter what. I'll write that to the right. And because it's a 1 to the 1,000, or 1 divided by 1/1000th, this actually simplifies to just 1,000. And if we look at the e value right here, you'll notice that it has a negative exponent. So that actually means it'll move up to the top. So it'll be e to the 1 divided by negative 1,000th. Now remember, 1 divided by negative 1,000th is going to change. It's going to change into e to the negative 1,000. Oh, but remember, that e was on the denominator already, so it should have moved to the top. So really what you're looking at here is 1,000 times e to the 1,000th. And you notice here that 1,000 times e to 1,000 is going to get exponentially larger. And if we chose a number that wasn't to the 1,000th power, say 10,000th, it would get even bigger. So what this means is that this function, as x approaches 0 from the negative side, is going towards positive infinity. As you can see here. Now, let's take a look at the graph. I know the direction said to use the graph, but I wanted to make sure I showed you both ways. If we take a look at the graph itself, you'll notice that as x approaches 0 from the negative side, you'll notice that it's going up, 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 up towards infinity. And if we come from the positive side, it's coming up, and then at 0, it goes down towards the 0 value, which is what we said in our original statement. So, that's all for now. You're going to have lots of time to practice this in class. Please feel free to ask questions and be ready to talk about it when we're in class. So that's all for now. I'll see you guys next time.